The next topic we're going to be discussing is compound unit analysis. Some measurements have a ratio or fractions of units. We've been looking at just single units, like converting 35 meters into kilometers. But what if I was looking at a speed limit sign where it said that it was 55 miles per hour? How would you convert this into meters per second if we were given that 1 mile is equal to 1,609.3 meters? Well, let's set it up. Now I started by writing what I was given, 55 miles per hour. And when they say per hour, I'm assuming that's for 1 hour. So I wrote that I have 55 miles per, means my division line, 1 hour. Now we want to get meters per second. So meters on top, seconds on the bottom. Since I'm given this right off the bat where it says 1 mile is equal to that many meters, I'm just going to do that first. And I obviously need to get rid of miles, so I need miles on the bottom. And it tells me that 1 mile is equal to 1609.3 meters. Now notice, because miles and miles are diagonal from each other, they cancel out. So right now if I were to stop, I would have meters, because that's the only unit on top, per hour. That's the only unit on the bottom. But I want meters per second. So let's put hours on the top here, and I need seconds on the bottom. So we got to figure out how many seconds are in 1 hour. Well, there's 60 seconds in 1 minute, and 60 minutes in 1 hour. So 60 times 60 is 3600 seconds. So that will cancel hours and hours. It doesn't matter that those hours are not right next to one another. Now we just need to get our calculators out and plug and chug. I got 24.59 meters per second. You might have rounded a little bit differently, and that's okay for right now because we have not talked about significant figures. But don't worry, when we talk about significant figures, your answer is going to look a little bit different. Let's do a compound unit problem here. A motorcycle is traveling at 105 kilometers per hour. What is the speed in meters per second? Why don't you pause the video right here and see if you can set it up. So here's where we started. I wrote down what we were given, and right off the bat I went from kilometers to meters. But if you decided that you wanted to go from hours to seconds first, you could have had these flipped around. It does not matter which order those are in. Your calculator is going to tell you 29.16672 meters per second. After we talk about sig figs here in just a few lectures, you're going to learn that it's 29.2 meters per second. But if you want to leave it as the longer number for right now because we don't know any better, that's all right. Let's talk about measurements. Measurements provide the information that is the basis for most of the hypotheses, the theories, and the laws in chemistry. Every measurement gives us 3 kinds of information. The size or magnitude of a measurement, so the number, a standard of comparison for the measurement, a unit, and an indication of the uncertainty of the measurement. Without these things, a number can be meaningless or confusing. Now in chemistry, we use an updated version of the metric system known as our SI units. Let's talk about length measurements. Let's say that I have a metallic solid rod. Ruler A versus ruler B. Let's look at the difference. We're saying this is A and this is B. Ruler A is by centimeters, whole centimeters. If I were to guess the length of this rod, I'm not going to say it's 4 centimeters. I'm not going to say it's 5 centimeters. But it's somewhere in between 4 and 5. But because my tool is only by 1 centimeter increments, so 4 centimeters, 5 centimeters, it's somewhere in between. That means I need to estimate to the 1 digit past. If I have a whole number, 1 digit past a 4 centimeter would be a tenths position, right? I'm going to say it's 4 point, I'm going to guess, let's say 4.2 for this guy. Let's look at ruler B. Here I'm going to say, hey look, I've got 4 centimeters, I've got 5 centimeters, but there's more tick marks. What do these tick marks mean? If I counted, there should be 10 tick marks in between each one. So I can be exact to the tenths of a centimeter. Here I could only be exact to the ones. If I can be exact to the ones, I would estimate to the tenths. If I can be exact to the tenths, what do you think I'm going to estimate to? Well, one digit past the 10th position, for example, if I said it's at least 4, and then I can go, 4.1, 4.2, it's past 4.2, but it's not 4.3. So it's somewhere between 4.2 and 4.3. I'm going to say, let's say 4.23. This is an estimated number. If I can be exact to the tenths, I estimate to the hundredths. So estimate one digit further than what your tool allows. So when we say that there's uncertainty in length, we're going to look at ruler A and ruler B, and we're going to say that ruler A has more uncertainty than ruler B. These rods are the same length, but back here I said, you know what, using this ruler, I said it was about 4.2 centimeters. But using that same rod, I said, oh, you know what, it's about 4.23 centimeters. So ruler A has more uncertainty. Ruler B gives us a more precise measurement because I'm able to be exact to the tenths and estimate to the hundredths of a centimeter. So it's a more precise measurement. There is more uncertainty with ruler A. Let's look at mass measurements. The mass of an object is the measure of the amount of matter that we are measuring. It's measured with a balance. It's not affected by gravity. Mass and weight are not interchangeable. In lab, we will be using mass balance scales that are electronic. Volume measurements. Volume is the amount of space that's occupied by a solid, a liquid, or a gas, and there's several instruments that we can use. In lab, we will be using graduated cylinders. We will be using syringes, burettes, pipettes, and volumetric flasks. So here's an example of what all of these look like. What's really important is that when we are looking at a graduated cylinder, some graduated cylinders measure to, let's say, to the tens. So 10, 20, 30, 40, and let's say I had a liquid that was in here right in between the 20 and the 30. If I can be exact to the tens, I would need to estimate and report my answer, the volume of that liquid, to the ones position, because that's one digit past the tens position, isn't it? If we're using a burette, and the burette here is by tenths, like that one ruler. So if I said I had about it was somewhere between the 1.1 and the 1.2, I'd say maybe 1.15. Again, if your tool is exact to the tenths, you go to the hundredths. If your tool is exact to the 100ths, let's say I was using a beaker and there was a 100 and there was a 200. If my tool was by the hundreds, what am I going to estimate to? I'm going to estimate one digit past that hundreds. I'm going to estimate to the tens. If my water was right here, I might say, oh, it's about 150, 160. It's okay if your estimate is a little bit different than your partner's, because that's telling us your estimated digit. Counting is the only type of measurement that is free from uncertainty. The result of counting measurements is called an exact number. Here are some things that are also exact. Whenever I say that 1 foot equals 12 inches, so when we have those quantities that says 1 kilometer is 1,000 meters, or 1 foot equals 12 inches, we do not use conversion factors when we are looking at significant figures and uncertainty. When we're counting something, that's an exact number. Significant digits do not apply to exact numbers. For example, if I looked at these quarters, I would count them and I would say there are 7 quarters on this slide. That's an exact number. Quantities derived from measurements other than counting are uncertain to varying extents. Those numbers are not exact. There are always practical limitations of the measurement process used. A measured number must be reported in a way to indicate its uncertainty. For example, if I reported that something was 4.2 centimeters, the person that's reading that would go, ooh, you know what? That's an estimated number. They knew it was at least 4 centimeters. It wasn't 5 centimeters. And it was about 0.2 of a centimeter. So the way that a number is reported, if I said 475 liters of something, the fact that the last number reported is in the ones position, that means that, oh, you know what? They estimated that 5 because the tool they were using was obviously only able to be exact to the tens position. So it was somewhere in between 470 and 480. So they estimated to the ones position. So again, you estimate one uncertain digit. Let's look at this graduated cylinder. We are going to look at this graduated cylinder and we measure at the meniscus. And look at this number. We're going to figure out what the tick marks mean. These tick marks between 5 and 10. I'm going to go 6, 7, 8, 9, 10. They are by ones. Tick marks are by ones, which means we will report our answer one digit past the ones digit, which is to the tenths. So we're going to zoom in here, then we're going to zoom in a little bit more, and we're going to say, well, it's not 20, it's not 21. I would say that's about 20 point, what would you say? 20.5 is pretty close to being where that meniscus is red. Let's talk temperature scales. Two temperature scales are commonly used in scientific work. We have the Celsius and we have the Kelvin. Now we're not used to that. In the United States we're used to using Fahrenheit. But in science we use Celsius and Kelvin. The Celsius scale is generally used worldwide for measurements in the laboratory. When calculations incorporate temperature data, however, Kelvin scale is almost always used. How hot or cold an object is determined by how fast the molecules are moving. Remember when we talked about kinetic molecular theory? If the molecules are moving fast, 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 we can measure that by temperature, and temperature is increasing. The average kinetic energy of an individual particle in motion tells us that temperature. If it's warmer, then those molecules are moving faster. If it's cooler, those molecules are moving slower. They have less energy. And again, we measure that with a thermometer. The coldest unit on the Kelvin scale is 0 Kelvin, which means absolute zero. It has never been reached because that would mean that particles were not moving. And particles have never been not moving. Here are some temperature conversion scales. To get to Celsius, we would take our Fahrenheit temperature, subtract 32, make sure you do that first in parentheses, and divide by 1.8. To get to Fahrenheit, we would do our Celsius temperature times it by 1.8, and then add 32. To get to Kelvin, we would need our Celsius temperature and add 273. Why don't you pause this and convert freezing and boiling temperatures for all three scales? And we know that water freezes at 0 degrees Celsius, and it boils at 100 degrees Celsius. Also see if you can do liquid nitrogen. If it freezes in tissue at 196 degrees Celsius, what is that in Fahrenheit and in Kelvin? Pause the video to find out. Let's look and see how you did on these conversions. I told you the freezing and boiling temperatures for Celsius scale. So let's go to Fahrenheit first. I took the boiling point, that's what this B is, and I did 100 times 1.8 and I added 32 to get 212 degrees Fahrenheit. There should be a degree sign there. Then to find the freezing point, I took 0 times 1.8 and added 32 and I got 32 degrees Fahrenheit. To get to Kelvin, as we can see right here, we take our Celsius temperature and add 273. So I took 0 plus 273 and 100 plus 273 to get my Kelvin temperature for freezing and boiling. Notice that there is not a degree for Kelvin, it's just Kelvin. Now let's look at the liquid nitrogen example. Negative 196 degrees Celsius is what the temperature is of liquid nitrogen. And so to find out that in degrees Fahrenheit, I took negative 196 times 1.8, added 32, and I got negative 320.8. And to find it in Kelvin, I took my degrees Celsius and added 273 to get 77 Kelvin. Why don't you take a second to pause the video here to figure out what the body temperature is in degrees Celsius and in Kelvin. Hopefully you figured out that it was 37 degrees Celsius and 310 Kelvin. Look at my work to see if it makes sense. Let's try one more example. Imagine that while traveling in Europe you come down with an illness. You only have access to a thermometer with Celsius temperatures, which tells you that your body temperature is 40 degrees. You want to convert this measurement to Fahrenheit. How do you do it and what do you get? Hopefully you saw that you have a temperature of 104 degrees Fahrenheit, which means you are sick and you need to go to the doctor. Now after talking about temperature, let's talk about heat. Heat is energy. we know that moving particles have energy. More heat means particles are moving faster. And when particles move faster, they hit other particles, so they can transfer heat by collisions. Now, the flow of energy from an object at a higher temperature to a lower temperature is how heat is transferred. Okay, energy is always transferred from a higher temperature object to a lower temperature object. Think about holding an ice cube. You hold an ice cube and what's going to happen? It's going to melt in your hand because you have a temperature of 98.6 degrees-ish. And that ice cube has a temperature of 0 degrees Celsius, which is 32 degrees Fahrenheit. So your warmer body is going to transfer heat to that ice cube, therefore making it melt. Now, heat energy is expressed in joules, capital J, which is the SI unit for energy quantities. Now, we're used to seeing nutrition labels with calories written on it. Just like, hey, in the metric system, we like to use meters, measure distances, but yet we're used to measuring distances in feet. So while the joule is the SI unit, we are also familiar with the calories. However, little calories are a teensy bit different than what we're used to seeing on those nutrition labels. One lowercase calorie is the amount of heat needed to raise 1 gram of water by 1 degree Celsius. Now, a nutritional calorie, notice that it's capitalized, is spelled with a capital C to distinguish it from the metric calorie. One nutritional calorie, so 1 capital C-A-L, is equal to 1,000 little calories. Or we can say 1,000 little calories is equal to 1 kilocal. So it's important to know that conversion. 1 little calorie is equal to 4.184 joules. The joule is inconveniently small for most uses in chemistry. So the kilojoule, kJ, is equivalent to 1,000 joules, and it's often the unit of choice. The dietary calorie, again, dietary calorie, we use capital C. So notice on your nutritional labels, it'll say capital calories. It's often used in the United States to represent the energy content of foods. If you were to be in a different country, you're probably going to see it advertised as kilojoules instead of capital C calories. The dietary calorie is equivalent to the kilocalorie, or 1,000 calories, like we just said. Thus, a breakfast cereal that gives you 100 calories of nutritional energy per serving provides 100 kilocalories, or 418.4 kilojoules. The U.S. Food and Drug Administration, the FDA, mandates that nutritional data, including energy content, must be included on almost all packaged food. When the Nutritional Labeling and Education Act of 1990 came about, it requires that the total energy from protein, carbohydrates, fat, alcohol, all be specified, which is all included in the nutrition facts. How is it determined? Well, initially, the method used was calorimetry, which we will be doing when we get later into this class. And in that method, we take a food product, we burn it, and the energy that's transferred as heat in the combustion is measured. And we're able to then calculate how much energy that food product has. So let's say we're looking at a box of Cheerios here. How many joules is 1 serving of Cheerios? How about you pause this and go back to our conversion factors and see if you can solve it. Let's see how you did setting it up. I took my 100 calories per serving, and that's with just the Cheerios. That's not including the Cheerios with milk. You will notice that cereal boxes will tell you that. And we know that for 1 capital C calorie, you got to have that down here to cancel out. There's 1,000 little calories. 1 little calorie is equal to 4.184 joules. Notice that little calories will cancel. That will give me a large number, 418,400 joules. This is why most often we refer to kilojoules for food energy. So 418.4 kilojoules in 1 serving of Cheerios. Now we've talked heat and we've talked temperature. What's the difference between the two? Well, think of this. Let's say that I have a little cup of water here, and I have a pot of water here, and I stuck my thermometer into both of them, and this says that it's 100 degrees Celsius, and this says it's 100 degrees Celsius. They're both boiling. However, which one would hurt more if it fell on you? Obviously, the larger pot of water, because there's more of it. Although both of these substances have the same temperature, just like both of these beakers, A and B, have the same temperature, The beaker on the right, just like this pot on the right, has twice the amount of heat because it has twice the amount of water. So heat is related to the amount you have of something.